Well, hello students. So today we're going to talk about probability once again. Crazy, I know, right? So we are going to get a little bit more complicated. I know the last couple days were kind of, easy lessons, and that was kind of just to get you guys used to solving math problems once again. So today we're going to be talking about probability of compound events. Now what a compound event is it is more than one event that's going to happen. So for example, if I were going to be flipping two coins, or rolling two dice, or I was going to be picking two different markers out of a hat, or choosing two random students in the class. Okay, so not just one event's going to be happening, but we actually have two here. So I'm going to read for those of you who have this page at your house, you can just follow along. For those that do not, this is the beginning of lesson 3 here. And this is called 2 nights of games here. So it says, imagine that a family decides to play a game each night. They all agree to use a tetrahedral die, which is a 4-sided pyramidal die, where each of the 4 outcomes is equally likely. And we are going to use this to decide whether or not we want to play a board game or a card game. So the tree diagram mapping the possible overall outcomes over 2 consecutive nights will be developed below. So we're going to make this tree diagram. Now, even though we are using a 4-sided die, here are my possibilities, okay? I only want to see what is going to happen on Monday and Tuesday and kind of compare them. So if these are equally likely here, on Monday and Tuesday, we have 2 different possibilities, okay? Now, what could happen on Monday? Well, first of all, we could decide to play a board game on Monday. Now, instead of writing the whole word board game, I'm just going to put B right here. Or we could play a card game. Now, I obviously love board games, so I would prefer a board game on Monday, but who knows what's going to happen. Now, what we're going to do from here is we're going to make a tree diagram to show what's going to happen. Now, if we decide to play a board game on Monday, we have 2 options for Tuesday. I could say, well, you know what, that was a lot of fun. Let's play another board game on Tuesday. Or we can say, you know what, let's switch it up. I mean, I clearly probably won the board game on Monday. Miss Franklin would attest to that. But we can play now a card game to give Miss Franklin a chance. Cool. And the same thing can happen here if we decide to play a card game on Monday. We can once again decide to play a board game, or we can switch, or we can keep it the same and play a card game. Now what this does is it gives us multiple outcomes of what we have here. So here are my outcomes that we have from this right here. The first option was we'll play 2 board games, or we play a board game and a card game, and we have a card game and a board game, and 2 card games. So even though we only had 2 options here, because we had 2 options for 2 consecutive days, we actually end up with 4 different possible outcomes. So depending on what my question could be asking, it could be saying, what is the chance of having at least 1 board game, or playing only card games? We now can compare it to those 4 possible outcomes. So it says, if BB represents 2 straight nights of board games, what does CB represent? CB stands for a card game the first day and a board game the second day. And here are all of my outcomes. We have 4 possible outcomes. So if I were to ask us a question, and I were to say, what is the probability of having at least 1 board game? At least 1 board game. I would take my number of possibilities. So in these examples, we are actually going to need my entire sample space right here. Here we played at least 1 board game. Here we played at least 1 board game. Here we played at least 1 board game. Here we did not. So that would be 3 out of 4. And once again, when it comes to probability, you do not need to worry about changing it into a percent, although we could, 75%, very easy, or changing it into a decimal. We can leave it just like that. Now I want to show a couple more examples now. For those, once again, that have this packet at home, you're going to recognize one of these examples, but I'm not going to do, I might actually do a couple other ones right here as well. So give me 1 second while I erase this. Show you a couple more examples of how tree diagrams can help us with understanding compound events right now. So very quickly, here we go. Let's not break Miss Franklin's board here. Cool. Okay, second option right now. We want to talk about a family here, and they just welcomed their second child. Now, it turns out that both children in this family are girls, but they are not twins. So we want to know what are the chances of having two girls in a family's first two births. Quite opposite of me, as I have two boys. But here we go, let's take a look. So we can draw a tree diagram. Our tree diagram could be going to the side or it could be going up and down. So in this case, I'm just going to draw one going up and down just so we can see it. So the possibilities are, let's talk about the first child right here. First child. Now it could be like my children, where the first child is a boy. Or we have a second option. It could be a girl. Okay? Now, going from this, we have, talk about our second child right there. If we have a boy at first, we could have another boy, or child number 2 could be a girl. And the same thing happens if we have a girl here. We could have a boy and we can have a girl. So in this case, knowing the probability of having two girls, we would look at this and say, well, look at this. Boy, boy, no, that was not having two girls. Boy, girl, also not. Girl, boy, no, but girl, girl, there we have one possibility. And to make it a little bit simpler, instead of having to write out every single time, BB, BG, GB, GG, I can just count my very last, I guess, the end of my tree diagram here and see that we had a total of 4 possible outcomes. So we have 1 out of 4 chance of having 2 girls. Okay, very simple. Now, if we were to continue this on, now we can do this for any number of children. It's going to change. And I know some of you are probably looking at this saying, well, we had 2, then we had 4 different possibilities. We probably would have 6 possibilities. Not quite how it works. If we were talking about a third child right now, in case I decided to have a third child, I could use this to figure it out as well. What are the chances of now having, what about 3 boys? Okay? I can almost have a whole basketball team here. That'd be pretty sweet. We have option there. If I had 2 boys, I could have a boy and a girl. But everything else also increases the chances here. A boy and a girl. A boy and a girl. And a boy and a girl. So not only do we now have a lot more possibilities here, we actually are now up to a total of 8 possibilities. So the chances of me having all 3 boys, probability of 3 boys, is now only 1 out of 8. So it changes that every single time. Now, this is a very easy way of visualizing it to see how the possible outcomes are going to work. It's not the only way of solving this. So give me 1 second while I erase this, and we're going to try one more way of figuring this out that might make it a little bit easier, especially once you start to understand compound events right here. So if I want to figure out the probability of having 3 boys and having 3 kids and having 3 boys, we can do this a little bit different. So I want to say the probability of having 1 boy is 1 out of 2. Probability of having a second boy, also 1 out of 2. The probability of having a third one be a boy is still only 1 out of 2, since I have a 50-50 chance every single time. So here we have 1 out of 2 times 1 out of 2 times 1 out of 2. 1 times 1 times 1 is? 1. And we have 2 times 2 times 2. 2 times 2 is 4. Times 2 is 8. So that's where we get that number from. And we can use this for any single type of problem that we want. So if I want to switch this up and say, you know what? What if we decide to roll a die? Roll a die. And we want to flip a coin. Okay? Think of this as almost like a carnival game. And I want to know the probability of rolling a 6 and getting heads. Now we could list every single possibility. We could make our tree diagram, which actually would not be too difficult. We only have 2 possibilities here when we flip a coin, and we only have 6 different possibilities when we roll a die. So we can see, we can actually visualize it going all the different options. Now to make this easier for me, I would say, well, what is the probability of rolling a 6? Well, rolling a 6, there's 6 different ones. Only one of those is a 6. 1 out of 6. How many? What's my chance of getting a heads? Well, that's 1 out of 2. So I'm basically multiplying them together. 1 out of 12 possibility right there. And it doesn't matter if it's 1 out of 6 or 1 out of 2. What if we wanted to say, what is the probability of getting at least a 2? Rolling at least a 2 here and a heads. Rolling, we'll do greater than or equal to 2 and a heads. Same thing. Options, I want to get at least a 2. I can get a 2, a 3, a 4, a 5, or a 6. 5 different options out of those 6. Times my still 1/2 chance of getting a heads puts us at now 5 out of 12. Not very likely, well, sorry, not very likely. Not likely to happen, but it also has a better chance of getting it right there. Now, if you need to, feel free to actually do your tree diagram, either vertically or horizontally. Make it a little bit easier to look at your outcomes, but you don't need to. You can just multiply them to get your answer. So make sure to hit the subscribe button. Make sure to answer all these questions that I have posted, and we'll post another video tomorrow. See you guys later.